Hello, hi everybody. Hope you can see me. I'm gonna put on full screen and lose you. So thank you for the introduction. I am indeed the lead product manager for access management for the NGAC platform. We're a platform that does systems of intelligence. We gather data, add AI and access management to it, make it secure. In any case, I'm here today to talk to you about how to secure your own API with your own graph. Now, I don't see you anymore, so if you have any questions, please feel free to add them in the Q&A, and I'll leave some time at the end and read them. So this is a developer conference for graph specialists. So I'm not too sure how much any of you know about IAM, or Identity and Access Management. So I figure I'd start by giving you some very bare basics so we can start on the same page. And a good place to start for a developer conference, I figured, was to look at the OWASP top 10 security issues. In case you don't know OWASP, it's the Open Worldwide Application Security Project. It's a non-profit organization that does some research on application security or software security and has a number of publications, one of which is the top 10 issues in software development for security. The number one issue is broken access control, and has been for since the last report in 2021. Now, what does this mean? We'll explore that, and through that, we'll get some basic understanding of IAM practices and how these apply to protecting your API. So the first example that OWASP provides, here's an example URL. It could be a URL to a web service or to your actual API. Now, the first issue that OWASP lists, it's pretty basic. As you can see, there's a query string at the end of this URL, and this query string specifies a particular account. So this is, for example, an API to request some account information. Well, as it turns out, more often than not, the account value there is not really protected or looked at. So in other words, as a requester, I can easily change this string to another and view another's account. That's not good, I'm assuming we all understand. It seems pretty basic, but it's the kind of things that are not right with application development for APIs these days. Now, in order to resolve that particular issue, we need to introduce the very first rule in access management, that is, you always need to authenticate your users. Now, authentication is like the front gate to your castle, is where you ask for credentials. And if your credentials checks, if the users are known, then you can let them in. Simple as that. Now, how to do that? Well, luckily, there are a number of open standards that help for authentication. And this is where this is what you should use, an open standard. Things like OpenID Connect or OAuth. These are probably words that you've already heard. SAML as well, or actually the more recent ones by the FIDO Alliance, WebAuthn, and in particular passkeys right here. Passkeys are the latest and greatest standard here, which allows you to log in users without requiring a password, and they're also phishing proof. Anyway, let's imagine that you've now implemented one of these standards and you can securely authenticate your user. Great. So once you have that and you know who your requester is, then you can easily get rid of this issue, because now if somebody requests an account that is not theirs, well, you can simply prevent that. So that's the first rule, always authenticate your users. The second rule, here's another example. These two URLs point to an admin page. Now, once your user is logged in, does that user have access to an admin page? In order to answer that question, you need the second rule, which is always authorize your users. Now, authorization happens once you've authenticated your users, once they're into your castle, and basically you want to know which rooms your users are allowed to enter, which staircases to take. In particular, you want to avoid this. You want to prevent this thief from stealing anything from your castle. So that's what authorization is: authorizing any action that a user takes in your own domain, in your own castle. So this is great. We have our two rules, but the problem is Even though these two rules really have been known in the identity and access management world for a long time now, we still see this. This is an infographic that showcases the world's biggest data breaches and hacks. This is about 4 months old, so it's still pretty current. They haven't published a more recent one yet. And as you can see, there are a number of rather big data breaches. This could happen through APIs or through all kinds of things. But what we know about these breaches, and this was true since last year at the very least, is that most of these breaches and attacks target identity. That is, they don't target the technology, which is in general quite solid, not the cryptography, but they target the weakest link in the whole chain, which is us, humans. Our identities are under attack. So why is that? Why is it so easy for these breaches to happen? Well, as it turns out, authentication is kind of broken, unfortunately. Well, our technologies and protocols and standards are sound, but what happens is now that we have a lot of actors, nefarious actors that are quite well known, very well organized, very well funded, and they do all kinds of very efficient campaigns that use phishing or social engineering just to attack identity. And the statistics are quite compelling. We see an increase in the number of such organizations, an increase in the number of stolen identities and credentials for sale. All of these statistics point to the fact that really we can't trust authenticated identities anymore, unfortunately. I'm not saying we should not authenticate users. We should absolutely do it. It's a bare minimum, but unfortunately, we can't trust anything these days, which leads us to the concept of zero trust. This means never trust, always verify. And at the very core of zero trust lies authorization. So again, authorization, the idea with zero trust is that you have to authorize every single request. So if you want to protect an API and prevent those attackers from doing too much damage, you have to authorize every single request. So some basic concepts about authorization. Some definitions first. In authorization, we talk about subjects or identities. So a subject is an entity that performs an action. It's an actor. It's essentially something that tries to connect to your API or your web app. And this actor needs to be authenticated and authorized. And typically that subject tries to access a resource, and a subject may also produce some data while navigating around your application or your APIs. It may produce some logs or generate some actions that trigger some data creation. Anyway, so some examples, of course, includes humans, web services, apps, IoT devices, AIs or robots. I think you get the idea. A resource, though, is an entity that is made available to one or many subjects. It's an entity that needs to be protected, and more often than not, it's an entity that is private, confidential, or secret. So what fits that category? Again, humans, because personal information is something that needs to be protected after all, but also web services, apps, IoT devices, and AI or robots. But in addition to that, we have some entities that don't actually perform any actions, never, such as, for example, files or your own data. So as we can see, an identity can also be a resource, but some resources don't necessarily act as an identity either. So now that we know this, typically in authorization, we are protecting resources for or from subjects. All right, good. So there are several levels of authorization. This is dictated by the granularity of the resource we're trying to protect. We have coarse-grained access control and fine-grained access control. So taking our API or our URL, the one that we looked at earlier, coarse-grained access control would be concerned with protecting the actual endpoint, so this part of the URL. And in addition to that, we would require a verb or an action. So in other words, for example, you would be wondering if a given subject can for example, post to this endpoint. Fine-grained access control, on the other hand, is concerned with the data level, the actual query string here, for example. Can this subject do a post, for example, on this particular account? In general, you probably need those two levels in order to enforce proper authorization. If your API is GraphQL, this is what it could look like. In both cases, you would need to protect the endpoint. But for coarse-grained, what you're concerned about is the endpoint is, of course, the action, and that is query mutation or subscription, and the actual type that is being accessed. For example, here, account. On the other hand, fine-grained is concerned with the data level, specific data. So you need a bit of both depending on your use case. Okay, great. So we know that we can protect at the higher level or at the very fine-grained level. So how do we do that? Authorization models. So the first model that has been around since 1992 and that probably everybody has heard about and maybe uses is role-based access control, or ReBAC. Role-based access control uses buckets such as these and places subjects, potential subjects, into various buckets. For example, managers, administrators, HR teams, etc., etc. Now, these buckets will have assigned to them a certain number of entitlements. Entitlements are access rights granted onto resources to these buckets. For example, managers, all the managers will have read and write access to file A, as in this example here. Or administrators will have CRUD access on file A and will be able to access a VM. The HR team will have HR admin access to an HR application, for example. Great, sounds great, actually. Simplify things. We put subjects into buckets and assign rights to the buckets. Great. The problem, though, with this approach is that over time, roles tend to multiply. And now a problem that a lot of big organizations have is that the more time passes, the more such buckets you have, to the point where nobody really knows who has access to what anymore. That's a big problem that a lot of big organizations face nowadays. So the problem is not really the ReBAC model itself. The problem is how it's been implemented for all this time, because all this time, ReBAC has been implemented as attributes on user entries or role entries. For example, here's an example of a user and group entry in an LDAP directory. As you can see, the member of is an attribute, a multi-valid attribute on the user entry, or the members of a group are also multi-valid attributes on a role or group entry. This attribute, this modeling as attributes has a problem. And this problem is that the entitlements are not apparent. Where are the entitlements? We don't know what they are. So if that's your model and that's how you store your data, and this applies also to SQL in general, those entitlements are actually part of the resource being protected. The resource knows how to interpret those roles, and it's kind of invisible. This is pretty bad because this leads to, again, that bucket problem. We don't know who has access to what. But here's what happens when we consider role memberships and roles as relationships instead. As you can see, now we're getting into the graph world. Once you start modeling your roles as a membership, such as user member of role, then we're not really dealing with ReBAC anymore. What we have in front of us now is relationship-based access control, or ReBAC. And what's good with ReBAC is that now we can model entitlements as well. Here's, for example, how you would model an entitlement. Now the entitlements are made explicit, and because they're essentially modeled as a graph, you can now easily see who has access to what, as you can gather or imagine. This is interesting because actually, back in 1992, in the original paper that introduced the concept of ReBAC, this is exactly how roles were modeled as relationships. This is actually a figure taken from that first article. You have users, members of a role, and roles have certain accesses to those resources or objects on this side. Interesting that we went from this to representing these as attributes, and in the way in that transformation lost this entitlement information. So if we were to look at some actual graph data, here's an example. We have a couple of users, we have a couple of resources, and a couple of roles. So for example, here using ReBAC, if we wanted to understand or see what user Alice Doe here has access to, what we would do is we would try to find all the possible paths from that user to the resource. So here we would only find resource 1. On the other hand, if we were looking at this user here, Bob Smith, well, Bob only would have access to these 2 resources. Pretty simple. Hopefully that makes sense. But we're not really limited to roles here. We can add a lot more things to this model or to this graph. For example, here we have a user that works for an organization that has a tenant that also owns some resources. No problem there. We can do more than just roles. And we can even go further. We can add attributes. So now we have attribute-enhanced relationship-based access control, or ReBAC. So it can become pretty interesting. So here at this point, there's another model that is quite popular and you might have heard about. It's attribute-based access control, or ABAC. And there is also a way to produce ABAC within a graph. And for that, we need to look at something called NGAC, or Next Generation Access Control. This is where it gets a little spicy. This is actually an ANSI standard. If you're interested, here are the references to all the various versions of NGAC. It's a standard that has been put forward by NIST, or the National Institute for Science and Technology in the US. And essentially what it is ABAC with graphs. So the way NGAC works is it uses a couple of subgraphs, 2 subgraphs. You have a user or subject subgraph that has user entries here and attributes. In this particular policy that we want to implement here, within a banking environment, we want to say that bank tellers can only access accounts between 9 a.m. and 5 p.m. So here we have some users, which presumably would be bank tellers or not, and they work in various branches. And we have a second subgraph, which is the object subgraph, or the resources that we're trying to protect. And here, these are bank accounts. Bank accounts also reside in branches, and there are accounts. In between them, we have these role nodes, not role nodes, but these policy nodes. So we have a role policy. The role policy identifies tellers and essentially links tellers to accounts. And we have a branch policy that says essentially that tellers can only access the accounts that are in the same branch as they work. And finally, we have what they call associations, which are relationships that dictate, that enforce the type of access that those users have on those accounts. So anyway, the way this works is exactly what I mentioned. A user is a teller and can have these permissions on these accounts through the role policy if they also work on the same in the same branch. Now, the time of day in this model is performed through what they call obligations. These are actual events that trigger. So when it's 5 p.m., you create a deny relationship between teller and account, which in effect denies this access. And at 9 a.m., you recreate or you remove that deny relationship. So anyway, all this to say that you can implement all kinds of access models using a graph. Now, let's go back to your own graph. Let's say that you have a graph data and you're trying to build an API. So as we've learned, you need to authorize and authenticate your users. How to do that? Well, ideally, what you would want to do is inject the identities within the graph somehow. So either that or create a separate graph that has kind of a digital twin of your data. And essentially, you will need to identify within this graph the identities of the subjects and the resources. These could be extra labels to your nodes or brand new nodes. And in between those, you would need to identify the possible path between the identities and the resources in order for you to apply one of those authorization models that uses graph that I just mentioned. So this is great. So once you've done that, what you have is an identity knowledge graph. So not only you have your knowledge graph, but now you've injected identity into it. So it's an identity knowledge graph, which gives you all kinds of benefits, identity insights. You have your data access control, and you can do your data management as well. But now that it's identity aware, you can actually tie it to your users and derive all kinds of insights. These types of users generally access these types of data, et cetera, et cetera. You can, if you build a RAG using an identity knowledge graph, you can actually tie it to identity in all kinds of ways. Sounds interesting, and it's the type of things that we do actually at NGAC. But anyway, so now that we know all this and we want to build an identity knowledge graph, well, how to go about building it? Well, here you have two options. You can build it yourself, or you can externalize authorization. Now, if you start building it yourself, depending whether if you're just working on your own and experimenting is probably okay. But if you're working in an organization, building it yourself essentially means building in your own silo. So not generally a good idea. And here's what. If you build it yourself, you're embedding the authorization within your own application. For example, here there are 3 applications and there are 3 users. There are employees, managers, or sysadmins. And depending on which application they are using, they don't have the same access rights. For example, here Bob is a manager and a sysadmin on application 1, but not application 3. If I'm looking at this system from the outside and the authorization is hard-coded or embedded in the application, well, I'm back again to this problem of who has access to what. There's no way for me to, know who has access to what. Also, if you build it yourself, you might end up building what we call spaghetti code, where a whole bunch of if-then clauses, really hard to maintain, really hard to prove, and in the end, it's quite costly because we probably have to debug a lot of these. You have to reproduce the code throughout all your applications. Might not be implementing the best practices. Well, leads to a lot of problems. Instead, a better way to do this would be to externalize authorization to dedicated applications that encapsulate all of these best practices and provide a common language for expressing those policies. Now you have a central place where all your policies are managed. So it's easy now to determine who has access to what, to trigger events in case of security alarms, and to do all kinds of compliance and reporting. So a lot of benefits from externalizing authorization: central policy management, a common policy language for all development, much faster development. You can now focus on building those APIs and the business requirements that you have. The policies become provable and auditable. They implement standards and best practices. Given that, here's the typical canonical architecture of an authorization system. On the right here, you have your resource to protect, for example, your API, and here you have your subjects. So there are 4 main components to an authorization architecture. There's a policy enforcement point, a policy decision point, a policy administration point, and a policy information point. The PEP is the proxy to the resource. Any request that goes to the resource has to go first to the proxy. The proxy redirects the request to the PDP, that is the brains of the authorization system. The brains can evaluate the access policies that first needs to read from a policy store. If this is a generic architecture, in our case, it would be just the graph, which combine the PAP and the PEP could be combined because that would be the graph. But in other authorization systems, they could be different. The information point stores additional data, like additional attributes, for example, that the PDP needs to use in order to compute a response. Great. So if this is your API, you could place an API gateway, for example, in front of it, or a proxy, Or you can even, the PEP can even be an if-then wrapper in your code, for example, that makes a call to an external PDP. Now, in order to ease things up in this ecosystem, in this whole architecture, the OpenID Foundation has come up with a new standard called Autzen. We're actually part of the Autzen working group as well, but this is a standard for communicating between the PEP and the PDP. So, in other words, if you are building an API and if you just want to build a simple if-then wrapper, you can initiate an Autzen request to any compliant external PDP. Fairly simple. And here's what the body of such an Autzen request looks like. This is a simple can Alice access resource type of question. You have a subject, a resource, and an action within the request body, and we can also provide a body, context. For example, here, user Alice, we're asking the PDP whether user Alice can read this account here at this given time. And the standard response is very simple, true or false. Actually, the full-fledged response is slightly more complicated. We can also get a reason why a decision was made back, an admin reason and a reason that is adequate to present to an end user. If you're interested in Autzen, here's a link to the actual specification. There are a number of externalized authorization systems that are compliant. Some are open source, some are not. It's pretty easy. You can go there and find more information about it. This should make these things much easier for you to integrate authorization into your API development. So to conclude then, never forget, always authenticate. Never trust any authenticated identity, always verify. Always authorize. Do externalize authorization because you're sure the best practices and the best methods will be used. You'll be able to develop faster as well. Use open standards, for example, Autzen, and you can use your own graph. You have a number of methodologies at your disposal, such as ReBAC. That's it. If you have any questions, you can feel free to reach out to me. I will minimize my screen, and we have maybe 3 minutes here for any questions that you might have. Let me see. I see a question here. Do you typically separate access graphs from asset graphs, or do you intermingle them? We actually intermingle them, or at the very least, we need to represent our resources within the graph so that we can protect them through ReBAC or ABAC or NGAC even. You don't have to, if you don't want to augment your graph with identities, you can create a separate graph, I guess, for that. And you don't have to pull all your data, but just maybe pointers to your original data. We just need some placeholder that are semantically identical to your actual data. Hopefully that made sense. So I don't see any more questions here, but if you have any more, you can feel free to reach out to me. Thanks a lot for attending this session and wishing you all a great Nodes conference.